So, let us start this lecture with a thought process about entropy. As the entropy of the universe is on increasing trend, that a lot of people have talked about it. The basic law of life is to organize ourselves meticulously, so that we can struggle against the entropy to sustain our life harmoniously on this beautiful earth. So, if you look at, we have looked at the basically the second law of thermodynamics very extensively and talking about the quality of energy. So, based on the quality of energy, then the energy can be divided into two categories. One is high grade energy, the other is the low grade energy. So, if you look at, we have classified this way. Can you give some example? What are the high grade energy? What will be the low grade energy? Any idea? We have already discussed, but let us now say that high grade energy means it will be mechanical work, it can be electrical work, it can be hydraulic energy, it can be wind energy, it can be kinetic energy, like, or kinetic energy from a jet, like in the case of jet engine we use it for producing thrust, right, or in the rocket engines, like. So, but if you look at the low grade energy is basically the chemical energy from the fuel, solar energy, geothermal energy, tidal energy, nuclear energy, whatever we really will be using as an energy source is basically low grade energy. So, the objective of the thermodynamic is to basically convert this low grade energy into the high grade energy in the best possible manner, so that utilization will be maximum. So, we have seen that the complete conversion of this low grade energy to high grade energy is not possible by a heat engine, according to the second law of thermodynamics. So, therefore, I mean like that means certain amount of heat has to be rejected, right, to the sink whenever a engine is taking certain amount of heat from the source, it has to reject certain amount of heat, so that the work can be done. And available energy, basically we can, from this we can say the available energy is basically part of the low grade energy, which can be converted into high grade energy, right, by a reversible engine. We call that amount of energy is basically available. So, for to consider that case, we will take this example, which is basically reversible engine. Of course, is the ideal one, but to discuss the point we are making, that it is absorbing the Q amount of heat from the source and rejecting Q naught amount of heat to the sink, which is at T naught temperature, and doing the W amount of work, right. So, now this case we need to find out basically what is the availability, right. So, if you look at, we know this what will be the efficiency for this engine. This is a reversible engine. Reversible engine means basically Carnot engine, right. So, by definition, that is W by Q is equal to 1 minus T naught by T, yes or no, in this example. So, I can write down that as W is equal to basically Q into 1 minus T naught by T. Can I not write down this simply? I mean, I will take this side here, what you call, I mean like, and then take this side, and that will be done, like, okay. So, now we can say that W is nothing but Q minus T naught into delta S, change in entropy. Can I say this or not? Yes or no? Because if I just take this thing Q into Q by T, and then we can say that is nothing but your change in entropy, q by T and into T naught that will give. So, if I look at this is the Carnot engine. So, therefore, it is taking the q amount of heat from the source and rejecting q naught amount of heat to the sink, and as a result, like the amount of energy which will be can be utilized for producing the work, the net work is W, right, is basically in this region. If you look at, this is the region, and this amount of heat which is going to the sink is q naught, this portion is known as unavailable energy, right. It is not available for you. Once it is go to sink, you cannot really take it out and do the some amount of work, So, and that is of course what we have seen a temperature, like your source temperature remaining constant, sink temperature is remaining constant, and we will now consider a case where you are taking some amount of heat from a finite body where the temperature is not remaining constant. For example, let us say you are having a very like a kind of a limited, let us say, boiler, and then you are taking some amount of heat from that for using in your engine, heat engine. So, then that temperature may drop out with the time. So, by that if you look at, I am taking some kind of a heat, right, and from let us say state 1, and it is taking heat and the temperature is going down till like the process is from state 1 to 2. But however, we are saying that it is rejecting q naught amount of heat to the sink, I mean in that temperature is remaining constant. So, the unavailable energy is here, and this is your what you call available energy, this portion, right. This is your available energy. So, we can write down that from the efficiency definition, right, that is dW is equal to eta into dQ, and we know that if it is a reversible engine, then I can write down dQ is equal to 1 minus T naught by T. So, if I will integrate this one, right, I can integrate this one, right, I will get W is equal to basically dQ minus T naught into delta S, and this Q minus T naught delta S is nothing but your available energy, and we call it also the useful work potential, right, and we call it is also the exergy. So, we will be using exergy and available energy interchangeable, both are same. Of course, in some places you may find there is a little difference, but we will not be using that difference. We will be saying that exergy and available energy is same. So, if you look at to our life, what is exergy then? What is the available energy? Is basically your talent, whatever you are having in the circumstances, you can use it, right. But if you will not use that, it will be useless. Even it may be with you, you may be a talented person, but it can't really express in terms of your productivity or the work. So, that is the amount of energy what is available, which can be converted into the useful work or the reversible work, that is known as available energy. So, exergy is a property of the system, an environment combination, not a system alone. Why? Because it is saying that it is giving to a thermal reservoir, right, which is at let us say some temperature, like is low temperature, right. So, therefore, it is a property, availability or exergy, whatever you call, we can use as a synonyms, exergy is a synonyms for available energy, and is a property of the system and its surrounding, right, or you call it environment in this case together. It is not a property of alone the system, because earlier we are saying the entropy is a property of the system, right. So, also the internal energy, right. So, the available energy we can consider another example, like let us say there is a hot body here which is at temperature T1 and there is a cold body at temperature T2 and the heat will transfer some amount of Q. Keep in mind that T1 is greater than T2. Okay. So, if I say that I want to find out during this process what is the change in available energy, right. So, keep in mind that the T2 need not to be the ambient temperature, it may be higher or it may be lower, whatever it may be, right. Let us say T1 is something let us say 1000 Kelvin and the T2 is 500 Kelvin, let us say for example, right. Then what will happen, some amount of heat will be transferred from the hot body to the cold body and we can consider this as a system. And naturally what will be its surrounding? If I look at this is my system, what will be surrounding will be this or not, right, for this, right. And the heat energy transfer through the temperature basically gradient, because T1 is greater than T2 in this case and it is an irreversible process, right. You cannot really get back those things, right, you cannot. So, is there any loss in available energy, right, because this is certain amount of energy is available here, right. What is that loss, what we need to look at it, loss in available energy. Let us look at that. If this process goes on like it takes place, the initial available energy what it would be, that is Q into 1 minus T naught divided by T1. What is T naught here? That is the ambient temperature, that is which will be, let us say for example, you will say here now our ambient temperature around will be something 40 degrees Celsius. So, it will be 40 degrees Celsius. If you go to winter it will be 25 degrees Celsius or 20 degrees Celsius, right. So, that is the ambient temperature. Right, and T1 is the temperature which is. So, therefore, this initial available, because if I want to sink I can use the air as in my sink, right, or I can take another reservoir and take a sink, right. That means beyond that I cannot really go, it will be not possible. So, therefore, initial available energy is a Q 1 minus T naught divided by T1. Similarly, for the cold body, right, what will be final available energy? It will be Q 1 minus T naught divided by T2, right, because once it will come in contact there will be some heat until the temperature T1 becomes the equal to T2. So, therefore, that is the energy whatever available at temperature T2, right. Therefore, we are calling it as a final available energy. So, the loss in available energy that we are using a short form LAE is equal to initial available energy minus final available energy. So, and that is nothing but Q 1 minus T naught divided by T1 minus 1 minus T naught divided by T1. So, if you simplify it, you will find it out, basically this is Q minus Q T naught by T1 minus Q plus T naught by T2 and Q, right. This will cancel it out. So, therefore, you will get T naught Q divided by T2 minus Q divided by T1. And if you look at this T naught and then Q by T1, 2 is nothing but your will be what? Will be the system, this one, is not it? Okay. So, and the surrounding will be what? Because you are taking the Q is from here, right, and that will be negative. When the heat is going out of the system is known as negative sign. So, this became basically what you call this Q which is going to the surrounding, it became positive. So, therefore, system and surrounding, like this will be basically is equal to q by T1 and this is q by T2. Okay. And that is nothing but T naught into change in entropy of the universe, system and surrounding. This is surrounding. Okay. So, for an isolated system, what it would be? We know the change in entropy will be of the universe will be greater than equal to 0. If I am system surrounding together, I am considering, that means there is no, and which indicates, if I look at this expression, right, it indicates the available energy at temperature T2, right, is less than the available energy at T1, and that is a obvious thing, because the energy whatever we are taking, this Q, that is the thing that is at higher temperature, therefore, that is a quality of energy is higher, therefore, available energy will be higher. We have earlier discussed that, right, that quality of energy will be dependent on the temperature. If the temperature is higher, the quality of energy will be higher. So, hence all the heat cannot be converted into work, that we have seen from the second law of thermodynamics, but however, all the work can be converted into heat by 100%. That means, if I want to convert the work into heat, it is 100% you can convert, right, but the reverse is not. So, let us look at the availability for a control mass system. We will consider a piston cylinder arrangement which contains gas at pressure P1 and volume V1, and there is some heat interaction here Q, right, and of course, the ambient pressure is P naught and T naught. And let us say when of course, it is at fixed, it is fixed, and then there will be fixed, I will release, this is a kind of a pin, I will remove this pin, right. What will happen? Removing this pin, piston will go up, yes or no, and it will go up till this pressure of this gas, right, is reaching the P naught V naught, P naught, the same pressure, right. And if you look at this is my state 1 and it is going to state 0, because that is the dead state. It is not, it cannot go beyond, unless you give work done, the piston cannot move up, because already reached the equilibrium with the ambient pressure. So, according to the first law of thermodynamics, that is Q10 minus W10 is equal to U naught minus U1, right. This is the 0 state and this is the first state, right, means I call it dead state in this case. So, second law of thermodynamics will be basically system plus change in entropy of the system plus the change in entropy of surrounding is equal to Sg, the entropy generation, right. And the system, what we call, we can say that S naught minus S1, that is the change in entropy of the system. Surrounding will be Q is going, that is divided by T surrounding. T surrounding in this case, what it would be? It will be T naught, yes or no, and Q surrounding will be nothing but Q10, right. And keep in mind, this is heat is going out, let us say, if I say from the system to surrounding. So, therefore, it will be minus, right, Q10 divided by T naught is equal to Sg, that means, right. From the equation 2, you can get change in entropy, that is S naught minus S1, okay, during this process, minus Q10 divided by T naught is equal to Sg. And I can rewrite, I can just multiply it here, the T naught in this case, and it will be T naught here and T naught. So, this will cancel it out, you will get T naught S naught minus S1 minus Sg into T naught is equal to Q10, right. So, if I combine this equation 1 and 3, right, what I will get? I will get basically in place of q 1 0, I can write down u naught by u 1 plus w 1 0. Can I not write down when I combine this equation? So, when I will just change that one, I will get T naught S naught minus S 1, right, minus S g into T naught, and minus W 1 naught is equal to U 0 minus U 1. Of course, one can say that the what is the work done here? The work done W 1 0, right, by the piston, right, is equal to U 1 minus U naught, change in internal energy, right, that is in change in internal energy, minus T naught S 1 minus S naught, that is a change in your entropy into multiplied by temperature, is minus S naught S g. S g is the entropy generation, right. So, that means this amount of work one can do, right. If it is a reversible process, so what will happen? We have not talked about whether reversible irreversibility, okay, till now. If it is a reversible process, what will happen? S g will be 0, right. This S g will be 0 for reversible process. S g will be 0, right. So, if we will do that, that is we can get that expression, reversible work will be change in internal energy, that is 1 minus U naught minus T naught S 1 minus S naught, right. Now, what is the useful work? Is it that reversible work is the maximum work, but what is the useful work for this system? This example, if you look at what it would be, because when the piston is moving up, right, in this example, what is happening? It is doing some work on the ambient air, yes or no? That of course we have not considered, now we will be considering, right. So, as I told, certain work is expended in doing work on its surrounding itself, the surrounding atmosphere air is being pushed, right. For example, if we take a piston cylinder here, right, and this is P naught, V naught, so there is something gas is there, let us say, and when it will go to the next one, right, it is here, this gas has been volume like P naught V naught, this volume will be changing, right, the piston has moved here, right. Of course, at this point this is P naught V naught and this is P 1 V 1 in the start with, this is going 1 to 0 state. Now, the useful work will be basically reversible work minus the work done on the surrounding by the piston in this example. Okay. So, the work done on its surrounding due to expansion of the piston or the movement of the piston, what it would be? It will be P naught into V naught minus V 1. Earlier it was start with V 1 and it becomes V naught, right. So, I can say that is the movement what is taking place, the change in the volume, right. So, that is the work done by the on the surrounding by the piston movement. So, the useful work will be become basically W u is nothing but your this portion reversible work, that is U 1 minus U naught minus T naught in the bracket S 1 minus S naught, that is the reversible work, right. That is the reversible work, right. This portion is your reversible work and this is your surrounding work, and I can write down this as U 1 plus P naught V 1 minus T naught S 1, right. I can separate it out and I can say that U naught plus P naught V naught minus T naught S naught. See, this is simple. So, this quantity, right, and we call it basically what you call availability function itself, right, that is the phi 1, and this says with the for the state 1 and this is the dead state, right. If you look at this, we call it as a dead state, right. These together will give me availability function phi 1. And when a system moves from 1 to 2, right, we have said that it is going from state 1 to dead state, that is the 0 we are calling. And when it will be, then what it would be? It will be nothing but phi 1 minus phi 2, right, and this term will be cancel it out in this case. So, therefore, we are getting U 1 plus P naught V 1 minus T naught S 1, right, and this is for basically phi 1, this is phi 1 availability function for the state 1, right. Of course, do not consider that because this is being cancel it out, right, and this is for the state 2, right. So, if you look at, I mean, we have seen that let us say you are at initial state, right, state 1, and this is my dead state, right, and it has you have gone from state 1 to the state 2, right. That means, what is the availability for so far state 1 is concerned? This is 1, right. For the availability for state 2 is concerned, this one, right. This portion is the availability for state 2. Are you people getting what I am saying? And then if we once, because all we are doing saying that availability is basically with reference to the dead state, right. I will give an example, right, which we generally happens, like if you keep the money in the bank, right, let us say 5,000 rupees, you can spend the money till what you call what 1,000 rupees. You can say, okay, bank cannot give beyond let us say 1,000 rupees, right. So, if you look at it has reached the dead state, right. So, kind of things, and if you look at like that means this is availability, right. Okay. And I will give another example. Suppose you are very alert in the morning time, right. I hope you are not, right. So, generally the people are very alert in the morning time, then in the evening time they will be very tired and you can't really look. That means you have reached a dead state. Then you will have to go for sleep and take rest, rejuvenate, and then come back and do work, right. So, availability basically will be saying that how much work one can do with respect to your reference, that is the dead state. And maximum useful work obtained in a process when a system comes to equilibrium with the surrounding, that is the dead state, what we consider as basically the maximum useful work. And the irreversibility, what it would be? That is the basically reversible work, right, minus the useful work, which will give me the irreversibility. This is basically easy because the entropy generation with reference to the temperature, that will give me what you call energy being lost in the irreversibility. And keep in mind that in the piston example, like if the piston is moving up and then doing some work on the surrounding, you cannot get it back, it is irreversible, right. So, specific irreversibility will be I is equal to reversible work minus the what you call the useful work, that is T naught into Sg, that is the specific, and its unit is kilojoule per kg. So, what we have seen, this is for the control mass system, but we need to handle also the control what you call volume or the flow systems, right, and we are considering the flow process to be steady for our this thing. So, let us say that there is a expansion of the gas in a turbine is taking place and it is entering at a at the inlet and it is leaving at the exit and some work is being done because the turbine expansion is going on and you can consider this as my control volume kind of things. And the reference here, this is your surrounding, right. If you look at this is your surrounding and some heat is going, right, and this is your dead state, you can say it is a sink kind of thing, right. This is your surrounding. So, for a steady flow process, we know the change in energy will be basically equal to 0 with respect to time. And we can write down the first law of thermodynamics as for the control volume, that m dot E into H E plus V E square divided by 2 G J D minus M I H I plus B I square divided by 2 G J D is equal to the amount of heat which is being transferred, that is the heat rate and also the work rate, shaft work, right. And second law of thermodynamics will be basically equal to the entropy what you call generation is equal to the m dot E S E minus m dot I S I into q dot surrounding T naught, and keep in mind that heat is going out from the system boundary, therefore, it will be negative. So, q dot by T naught, q dot surrounding nothing but q dot by negative. Now, what we will do in place of this, I can say I can multiply this equation by T naught. So, this will be T naught. So, if I T naught, this will be cancel it out and then you will multiply it here and then use this in equation. If I say this is equation 1 and this is equation 2 combined, we can get a relationship, that is shaft work is nothing but the enthalpy change and then kinetic energy and potential energy, and also there is a new term which has come T naught S I, of course multiplied by the mass flow rate at the inlet, and similarly in the exit, this is at the exit, right, and minus T naught S dot G, right. So, if for a reversible process, of course, the entropy generation will be 0, right, because this is a reversible process. So, you can get the reversible work is basically the change in energy and also the what you call, we will define this term availability, right, we will be doing that. So, this is also change in availability at the exit. So, the reversible work that is the availability or the exergy can be expressed as basically the what you call the availability at the inlet minus the availability at the exit, and this psi I have used, that is basically availability function, and people call exergy function also. And keep in mind that this we can basically the availability function is written with respect to in the similar way what we have done for the control mass system with respect to dead state. These are all dead state, 0 means dead state kind of things, right. And if you take inlet and outlet, this term will be basically cancel it out. So, if there is a multiple stream device, right, heat exchanger kind of thing, what will be the reversible work, right? That will be nothing but your entropy, what you call availability function change for the, of course, if it is several kind of a what you call inlet will be there, then it will be, if it is let us say n number of inlet, then you can say availability at the inlet, and similarly availability in the n, it can be different, like at the exit, and you can get what will be the useful work basically, right. In this case, the what you call reversible work and the useful work is the same, right, because And irreversibility, you can calculate W dot reversible minus useful is equal to T naught S g, right, because in case of reversible work, right, what it would be, because S g will be 0, right, S g will be 0 in case of reversible work, right. So, therefore, T naught S g is coming, right, and specific irreversibility is nothing but reversible work minus the useful work, that is T naught S g. It is similar to that of the control mass system, right. So, question arises how to evaluate performance of a device, right, that we need to work it out and find it out, because second law of thermodynamics will help us to evaluate, and what is the extent of improvement we can do by what you call minimizing the irreversibility, that we can do. So, the performance of a device can be evaluated in terms of thermal efficiency and COP, that we have seen. COP is basically for the refrigeration system and the heat pump system, right, whereas the thermal efficiency will be using for the heat engine. And the maximum work from a device can be achieved basically by improving the thermal efficiency and also using higher quality of energy, right. That is the one way of improving or maximizing the work. So, let us consider a turbine here, and in which the gas is expanded, right, from P1 T1 to P2 T2, and some shaft work is being produced. If you look at, this is the constant pressure line, and P1, and there is another constant pressure line P2. And if you look at this expansion is taking place from state 1 to 2, this is known as isentropic expansion, right. This is isentropic expansion, where the entropy is remaining constant. In this case, S1 is equal to S2S, like entropy is remaining constant here, right. And this is the actual process, actual expansion, that is from state 1 to state 2, right. So, therefore, we can define the efficiency, and this is an isentropic process, that is W ratio of W divided by the reversible work done, right. And what is this work done? If I consider there is a change in kinetic energy, change in potential energy is equal to 0 and steady flow process, then I will get W is nothing but H1 minus S2. And for reversible process or isentropic process, that will be H1 minus S2S. So, if you look at this portion is the isentropic expansion, that is the ideal, and H1 minus S2 is the real. So, if you consider let us say there is a heat engine which is having efficiency of 30%, right, and there is another heat engine which is operated between what we call another source, that is which is at 1000 Kelvin, and of course, the sink is same for both the engine, then it is also efficiency is 30%, right, both are having 30% efficiency. And that and whereas like you will see that from the Carnot efficiency, right, we will say that this efficiency for the which is operated the heat engine A between the source temperature of 600 and sink temperature 50%, whereas the for the heat engine B it is the Carnot efficiency is basically right 70%. That means, in which engine case there is an like more scope for improvement? Definitely the heat engine B, right. There is a lot of improvement can occur, although you can say look both are having 30% efficiency, right. That means, there is a lot of scope availability, you can say Exergy is available for you to exploit it for improving its efficiency. So, therefore, we need to define a second law of efficiency, that is the ratio of useful work divided by change in availability. This is basically change in availability, right, or the exergy. That is exergy, and which is equal to 1 minus T naught Sg divided by psi minus I 1. What is this one? This is basically irreversibility, T, right, and we will have to basically minimize this irreversibility such that we can get a higher second law of efficiency. Of course, that is one can do. So, we have of course, discuss about that change in kinetic and potential energy 0. So, let us look at a compressor, right. In the compressor, the what you call the efficiency, first law of efficiency is nothing but your what you call reversible work done, work input to the compressor divided by the actual work input, right. So, if you look at, if I want to do this thing H and let us say S, what will happen? This is the pressure line. So, this is 1 to 2 and this process is your what you call 2S and this is 2, right, and this S is corresponding to the isentropic process 1 to 2 where entropy is remaining constant and this is the actual process. So, therefore, S2S divided by S2S minus H1 divided by S2 minus H1 for the compression, right, and this efficiency we call it as basically isentropic efficiency, right. This is same as that of the compressor, and of course, you can call it as a first law of efficiency or isentropic, because the reference is your isentropic process. So, second law of efficiency will be reversible work, the same definition divided by the useful work, that is nothing but your psi 2 minus psi 1, that is the change in availability divided by the useful work. And the if you look at the second law of efficiency, one can solve out exergy lost divided by the exergy supplied kind of things, right. And the second law of efficiency, one can say that like is nothing but your what you call the W by W reversible, right, and W reversible from the Carnot engines, we can say write down QH 1 minus TL by TH, and this one is nothing but your the efficiency, first law of efficiency, right, divided by the Carnot law of efficiency will give you the second law efficiency. And similarly, for the heat pump or the refrigeration, you can think of COP divided by COP reversible will give you the second law of efficiency for the heat pump or the refrigeration system. So, if we will consider this as a basically heat engine and which is the source is 1200 Kelvin, from which the QH amount of heat being what you call taken, and it is QL amount of heat being rejected to the sink which is at 300 Kelvin, and it is doing the work W, right. So, the first law of efficiency in this case, what it would be 1 minus QL by QH, and which is happens to be 75%, let us say, right. And if you look at the Carnot efficiency, right, that is a reversible engine, right, which is nothing but your Carnot, which is equal to 75%. That means, what it would be then second law of efficiency? Second law of efficiency is the ratio of the first law of efficiency divided by first law of efficiency for the reversible process or the Carnot. Therefore, it is 100% efficient, right. Second law of efficiency is 100%. right. Of course, if you get that is very good, like you basically what it says that that there is no scope for any improvement of this engine if the second law of efficiency is 100%. In other words, it says also that this is a reversible device, otherwise it cannot really happen to have 100% efficiency, right. So, let us consider the amount of what you call, we will say this is our hot tea, right, which is at certain temperature, right, and it is you can take system boundary as the hot tea itself, cup itself, and then q amount of heat is going. If it is going out, you cannot really to the ambient temperature, which is at T naught, right, P naught kind of things. So, then that amount of heat is basically going west. That means, this heat is cannot be really can be utilized because it has gone to the dead state. So, second law of efficiency of naturally occurring processes is 0, as none of the work potential is recovered, right. So, you cannot really recover kind of things. So, if you look at like if I consider that basically the availability concept, like I mean lot of amount of energies are available. For example, like if you consider the sea is having lot of water, like, and then it is at temperature, let us say ambient temperature. Of course, in the like this thing, if you consider multiply, that will be something billions or not billions, it will be several billion of joules will be there, but we cannot utilize it because its availability is almost 0, right. So, therefore, we cannot. Similarly, if you consider the air around the earth, it is having a large amount of energy. If you do a calculation, let us say how much amount of air will be there in the around the earth, and it is at temperature T, and then you multiply it with the Cp, and then you calculate, it will be enormous. Even if you tap that 10%, 20% energy, we will solve the problem of energy scarcity, like energy whatever, but those we cannot use because those are availability is 0, dead state. So, I mean like this is the things what will be having, that what you call the availability concept and exergy, and it is very useful things for to find out the what you call how you can improve the performance of a particular system or a process by what? By basically identifying the causes of irreversibility and eliminating them, and then you can know. So, this also talks about the quality of energy kind of things we have seen. So, it is a very useful concept, and which is being used to optimize the system and also the processes such that, and with this we will stop over. Thank you very much.